All right, let's take a look now at section 7.2. And let's talk about volume. And we're going to do it using what's called the disk method. In a later section, we'll see another method called the shell method. Although they do give the same kind of result, namely the volume of an object, they are used in different instances where one may be simpler than the other depending on your circumstances. So what we're going to be talking about is volume, the amount of space that something takes up. Now, for simple objects, volume is very easy to come by. You have volume formulas for spheres and cylinders and cones and rectangular solids. But oftentimes you're going to have solids which may not have a regular shape. So in order to see how that works, let's take a look at a familiar object. Let's talk about a box, a cube, right, or a rectangular solid. Now, instead of having an actual rectangular solid, I'm going to have something like this. I have a deck of cards. Now, notice this is a rectangular solid. It has it's got a rectangular face on both sides. It's got a rectangular side. It's got another rectangular side here. That's a rectangle, right? 4 sides, parallel top, parallel bottom, parallel sides. That's a rectangle. All right, it's a rectangle there. And on the other side, it's a rectangle. This is a rectangular solid because no matter what side you look at it from, it's got 6 different sides. Top, bottom, the 2 sides here, the front and the back, all of them are rectangles. Now, I could measure this rectangular solid and find its length, its width, and its height, and multiply those all together. And of course, that would give me the volume. But what we're trying to do is we're trying to see what happens when you have an object which you don't easily find. So here's the idea. You have a solid. Okay, that's 3-dimensional. Now, 2-dimensional objects don't have a volume. If something is perfectly flat, it has a length and width but no height. So imagine that I'm going to take this rectangular solid and I'm going to slice it. In fact, you don't have to imagine it. I'm going to slice it right here. There you go. I pull out a single slice. So now, if this slice is thin enough, you can say, well, it doesn't really have a height, right? It's just flat, length and width. Now, of course, this actually does have a height. It's very, very thin, but it does have some amount of thickness. But here, let's pretend this is an ideal situation where this is just length and width. Okay, well, notice that if I find this length and this width, that gives me an area. Okay, well, that's not a volume. But now, if I say, well, yeah, but remember, this actually does have thickness. It's just extremely small. Okay, so then I could find the volume of this thing. It would be length times width times, well, I guess height, but it would be a very, very small height, very, very thin. Okay, well, let's say I do that again. I take another slice. Now, of course, since this is a rectangular solid, each of the slices are exactly the same. If I take these slices one at a time and start stacking them together, eventually they'll add up to give me the rectangular solid. And I'm not going to do that 52 times, am I? So here, what we have is, okay, I have a solid whose shape I know to be a rectangular solid, but instead of thinking of it all at once, what I'm going to do is I'm going to think of it one slice at a time. And if I can find the volume of that slice, then adding them together gives me the volume of the entire object. Now, for a rectangular solid, that seems unnecessary, and in fact, it is unnecessary. We know how to find the volume of this. But let's say we had a more irregular shape. And although usually I give examples either drawn out or through a graph, this time my example is going to be just a little bit different. Imagine you have this shape. In fact, don't imagine it. Just take a look at it. Here I have a peach. It's a piece of fruit that I just pulled out of my refrigerator. What's the shape of this? You say, well, it's a sphere. No, it's not. It's got that dip in the middle. It's got that line right here. It's got bumps and wrinkles. That is definitely not a sphere. Spheres are smooth all the way around and uniform. So let's say I was going to look for the volume of this peach. All right, well, I don't know. I don't have a formula for the volume of a peach shape. I'm not even sure what you would call that except maybe a peach shape. So what should I do? Well, I could do the same thing. I could slice it. So here, a mathematical kitchen knife. What I'm going to do is I'm going to just slice into it. And I notice that when I slice, assuming I slice thin enough, the shape is something that is maybe a little easier to deal with. If I slice this very, very thin, Notice that's just a little disc. Here I have an oval, and I know how to find the area of an oval. Now here I've sliced this very thin, and I'm actually surprised I was able to get it that thin. So if I do this over and over and over again, notice each one will have a slightly different size. Here you're supposed to imagine that they're all uniform in thickness, which I'm actually doing a pretty decent job. I'm surprising myself that I'm doing that. Then what I'm going to do is I'm going to find the area of each of these surfaces. All right. Now, of course, each one has a thickness, but it's very, very thin. So basically, I'm finding an area times a very tiny thickness. If I then have enough of those, it will contribute. There we go. I knew I was going to mess that up sometime. If I take enough of these and put them together, then I'll form the volume of that peach shape, which again is not something I have the volume of. I don't have a formula for this, but I do have the ability to find the volumes of each of these pieces because each of these is a disk. It's something simple for me to work with. This is what's called the disk method. This is a bit of a messy illustration of it, but the disk method essentially says, all right, do you have an object that you know how to find the volume of? Well, sure I do. Okay, fine, then just find the volume. Just use your formula. Oh, but if you have an irregular shape, something that you don't know how to work with, what we're going to do is we're going to slice it into very thin slices. We can then find the volume of each of those slices, and when we add them together, they will create the entire peach, the entire object whose volume we're looking for. Now, to make things a little simpler, as I mentioned, we can have an object whose slices are small rectangles, rectangular in shape, or discs, or small triangles, or really anything. But we're going to restrict ourselves to the class of objects where when we slice them, we're going to end up with small discs, circular cross sections. So let's take a look at an example of how that's going to work. So first, an illustration. Consider the following object. You say, well, that's not an object. You have a grid here. Okay, well, I'm going to draw an object. Okay, something like this. Well, again, that's not an object either, at least not something I can find the volume of. Notice that's two-dimensional. So I thought you wanted 3 dimensions. You want to find a volume. Here, the best I can do is find area. So here's how we're going to guarantee that all of the objects that we talk about in this section have circular cross sections. We're going to build them so that they do. Here, I'm going to have a function. Let's call this f of x. Now, I want this function to go all the way down to the x-axis. That won't always be necessary. We'll see in some later examples, but for now, we'll start off simply where it comes all the way down to the x-axis. So now, what we're going to do is we're going to take this object and we're going to rotate. What do you mean rotate? I mean, okay, I know that's on a flat surface, but imagine that this is stuck to that axis. Imagine it's a physical object actually made of cardboard or paper or something. So now what I'm going to do is I'm going to start having this spin around. I'm going to have this rotate. So this object is going to swing up toward me. So for example, if I had my finger right here, okay, it's not currently touching that object, but when it starts to spin, in a moment, it'll actually come up and hit my finger. You'll notice that as it goes around, these points on this curve will trace out a solid object. It'll look something like this. So this point will come all the way around and then back around that way. Same thing with this point. It'll come out, and then once it's all the way this way, it'll continue rotating and around the back side. So it looks like this, and like this, around and around and around. If you're having a hard time visualizing that from my maybe not expert drawing, I'm an expert in mathematics, not in art. Here you have kind of like a football shape. It's actually, yeah, it's the shape of a football, American football. You know, the one with the laces on the outside, right? So here, every one of these cross sections is a disc. Now notice, this disc is much smaller than this one. This one's smaller than this one. The one in the middle is bigger than any of the others. Okay, so each one of these, and here I'm going to go ahead and make one very, very thin here. we could take this football and slice it going this way, slicing straight up and down, and end up with a bunch of little discs. Okay, well, let me take one of these discs and pull it out. So let me grab it and pull it out over here. And what I have is a little disc. Now, that little disc has a thickness, and it has an area that we're looking at. So you can kind of imagine this as being a coin, right? It's very, very thin, but it does have some level of thickness. And here it has an area of its face. It's a coin, a disc. Okay, well, how do I find the volume of this? Well, notice this disc is basically just a cylinder, and I know the volume of a cylinder. Volume of a cylinder is given by volume is equal to, we're going to take the area of the face, the area of that circle, which is pi r squared, multiplied by the height of the cylinder, which in this case, it's a very small height. It's very, very thin, but it is still a height. Okay, well, this r, what is that r? Well, that r is the distance from the center of that disk to the outside. And you say, well, sure, that's what r always is. It's the radius. Well, yeah, but on our illustration, what is that? Well, again, it's the distance from the middle. Well, what's the middle? Well, it's the x-axis, right? We're spinning around the x-axis, which means the x-axis must be the middle. And that we want the distance from the middle, which is the x-axis, to the outside of my curve. Well, the outside of my curve was given by these outer points on the outer edge of that football. It's given by the skin of the football. So this radius is really the distance from the x-axis to the curve. But that's just called the y-coordinate, right? The y-coordinate tells you how far up this is. Oh, but that's your function, right? After all, that's what we mean when we say f of x. We mean y is equal to f of x. That's how function notation works. So here, this r is really just your function. So here we can write this as pi times the function of x quantity squared times your height. Oh, hold on. What about height? Well, we can write height a slightly different way as well, because this height is very, very tiny little height. This thickness of this little coin, that's our height. Okay, well, the thickness of that coin is just that thickness across here, that little tiny amount of distance from one slice to the next slice. Okay, well, that's a little tiny change in the x direction. That's a little tiny, if this was x equals 1, this would be x equals 1.05 or something. Just a little tiny distance across the x-axis. But if you think back to Cal 1, what do you call little tiny differences across the x-axis? You call them delta x. So here, this h, you can think of as delta x. Okay, so that's pi f of x squared times delta x. Okay, so this is the volume of that one little disk. Okay, so now what? Well, now I want to find the volume of all the disks. Okay, well, whatever. They're all going to work the same way. I'm going to take the radius, which it's going to change, but whatever. I know the function will tell me what the radius is every time. All right? The function's smaller over here. Well, okay, well, then that'll tell me the radius is smaller. So here, all of these are found the same way. But once I find each one, I want to add them together. I want to stack them to form the object. Okay, so that's the volume of one cylinder, one disk. The volume of the entire object, volume of the whole solid, is equal to the sum of the volumes of the disks. I'm going to say the slices. Well, here that's a nice sentence, but this is a calculus class. It's the sum of the volume of the slices. It's the sum of pi f of x quantity squared delta x. Well, yeah, but that x is different each time, right? Here's your first x, here's your second, your third, your fourth, your fifth, all the way out until you get to the end. Okay, so these x's are going to differ. Okay, well, let me label them. Let me call that, x1, x2, x3, x4, x5. I'll use the generic symbol I, x sub I. Now, I can be a 1, a 2, a 3, a 4, a 5, and so forth. Well, what I want to do is, and over here that should be the same thing, delta x sub I, the little change across each of the different little disks. And what I want to do is I want to add these all together. I want to start from x equals 1 up to x equals 2 to 3 to 4 to 5 to... Oh, well, that just means I want I to start from 1 and go all the way out to some value of n. All right, how many slices did I cut that up into? Well, I cut it into 50 slices. Okay, so I want to add up starting from the first up to the 50th. Okay, so what does that give me? Well, remember, each of these is a cylinder. Oh yeah, but look, that thing's curving. Cylinders don't curve, they're flat. Oh, that's true. So here, this isn't exactly the correct volume, because what I found is I found this. I found all these little coins stacked together, and notice that because the coins are not curved this way, right? They're perfectly flat, then I don't actually have a football shape. What I have is some, well, there's a little bit of gap here and here, everywhere along the edges. I would have something like this. All right, I have a collection of coins here, and you note that they does have a wider one in the middle, and as you move to the outside, they get less wide. So it does start to have that kind of football shape where it's bigger in the middle and smaller to the outside. But you notice that along the top edges, since these are perfectly flat, here and here and here and here, they don't have that gradual shape that I was supposed to have. They don't have that curved shape along the outer edge. Here they just have, okay, here's a flat edge and then another one and another flat edge all the way out. Okay, so why doesn't this have that nice smooth shape? Because these are too thick. If you could imagine I had thinner coins, they would fit closer together and I wouldn't have such a big gap from one edge to another. So the thinner I make these little coins, the better it's going to look, the closer it's going to look to having a nice, smooth, rounded edge. Oh, well, in order for me to have thinner coins, I'm going to need more of them. So here, this end needs to get big. I can't just slice it 5 times. I have to slice it 10 times or 100 times or 1,000,000 times. Or, well, you know what? No matter how many times I slice it, it's still not going to be perfect. What I need to slice it so many times that these become so thin that there's no gap at all. Oh, so I need n to become infinitely large. So here, the volume of the solid is equal to the sum of the slices, which is approximately equal to this sum here. So this isn't exactly right. As you see, it's close, but it's got all these gaps. If you want to make it exactly right, what you want to do is you want to take the limit as n approaches infinity of the sum as I goes from 1 to n of pi f sub x, f of x sub I quantity squared delta x sub I. But if you recognize this from Cal 1, that's an integral. Here we can write this as the integral from a to b, where a is the beginning, right here, this left side, and b is this right side. The integral from a to b of pi times f of x quantity squared, and this small delta x becomes an infinitesimally small thing. It becomes dx. Since pi is a constant, the linearity of integration allows me to just pull that out, and so we can write this as the volume is equal to pi times the integral from a to b of f of x quantity squared dx. This is the result of using what's called the disk method. Oftentimes people will just say this is called the disk method. Really, this is not the disk method. The disk method is this idea of slicing things into disks. But if you then compute the volume using those disks that you sliced, you end up using this formula. So most people just say, oh, this formula is the disk method. Technically, they're different, but no one really seems to pay attention to the difference. So let's take a look at an example of that. Let's see here. Let's find the volume of the following object. We're going to take the curve y equals the square root of x. And then we're going to revolve that around the x-axis. So this is going to start to spin here. All right, so we're going to take this curve and we're going to find the region from 0 up to, let's just say 0 to 4, because why not? All right. So once you have that shape, you're going to start to revolve around the x-axis. So this point will come around, and this point will come around, and this point will come around, and around and around like this. So eventually you get this shape here. It's a dome shape. It really is. Imagine taking this football up here and then just cutting it in half and only keeping the right half. Or I guess the left half. Okay, so that's 0 and that's 4. And what we're going to do is we're going to find the volume of this. Okay, so here we're going to use the disk method. In a later section we'll see another method that we're going to use aside from the disk method. They're interchangeable, meaning they do give you the same result. However, depending on the problem, sometimes the disk method will be easier and the other one will be very complicated, or sometimes the other one will be easy and this one will be complicated. But for now, we're working with just this one. So that's going to be pi, volume, is going to equal to pi times the integral from a to b of f of x quantity squared dx. In this problem, we're given everything we need. Your A and your B are simply the left and the right boundaries along the axis of rotation of your shape. So here that's going to be from 0 up to 4. Our function, that's giving us the distance from the axis up to the curve, and that's your f of x. Now don't forget you're squaring that. And then we're integrating all that with respect to x. And that's it. So here we can write this as pi times the integral from 0 to 4. The square root of x squared is just going to give us x. That might cause a problem should we have any negative values of x. We could have imaginary values. We might end up having the wrong sign, things like that. But here we have everything positive. So no problem. Square root of x squared is just x, so long as x is positive. And now this is a nice, very simple integral. The pi is a constant, just remains as it is. The antiderivative of x is going to be x squared over 2, and that's going to be evaluated from 0 up to 4. That's going to give me pi times, that's 4 squared, well that's 16 over 2, minus, and that one's just going to give me 0. Right? 0 squared over 2 is just 0. So this will give us 8 times pi. And that is the volume of this shape here. Now you might say, well, that's way too easy, right? Is that always going to be like that? Well, sort of, but sometimes we have to figure out a few things on our own. So here we're given absolutely everything. Hey, there's 0, there's 4, there's your function. You just plug it in there, there, and there, and then integrate. Let's take a look at some more examples where things are not quite as apparent, but you'll note that it all does work out the same way in the end because we're going to be using the same method. So now let's consider this object. So we're going to take the curve that looks like this. I guess I shouldn't have drawn it that far out, but okay. Here's a curve, and here's another curve. And we're going to rotate this object around the x-axis. So just like the other object, we're going to revolve it around the x-axis. Notice, however, that now your surface does not go all the way down to the x-axis. Before it did. Right? Here, your surface went all the way down to the x-axis, and then we revolved it. And same thing here. This surface went all the way to the x-axis, and then we revolved it. This one does not do that. Okay, so how is that going to differ? Well, first of all, let's draw it out and see what the object looks like. And then once we're done doing that, then we'll see how we can adjust our integration to compensate for that change. Okay, now, this is about to start rotating. Notice, if I were to stick my finger right there, this object would never hit it because it would rotate out, around, around, and around. But since there's nothing here to rotate, this is always going to be hollow. So if I take this object and rotate it around the x-axis, okay, this curve will give me things that look like this. But then this line here, the gap between this x-axis and this line, remains down here. So that's going to remain hollow, which means this solid region will revolve around the x-axis, and that'll give me a solid region out here. But the space in here, this cylinder, is going to be hollow the entire time. Note that it's not just this upper edge and this lower edge. You have everything in between. This object is all the way around the outside, and the only thing that's hollow is the cylinder on the inside. So what that object will look like is something like this. Right? It's going to have a hard outer shell, and it is all the way around, but on the inside, it's going to be hollow. So if I turn it on its side, I can see all the way through it. If I turn it on its side, I can see through it. It's hollow through the inside, but the outer walls have a thickness. And you'll notice that all of my cross sections, if I slice along this direction, I'm going to end up with these little discs. But you'll notice that the discs are hollow through the middle. So here, if I take one of these slices, it's going to look something like this. And here, let me draw one out. I'm going to take that one very thin slice from the middle, and I'm going to pull it to the side, and it's going to look something like this. Okay, it's still a disc, it's still a circle, like that, and it still has some amount of thickness, so something like this, like a coin. Oh, but it's hollow in the middle, so it'll look something like that. There's a bunch of names for things like this, where it's like a coin, it's like a disc, but you have a hole in the middle. There's different names for this kind of an object. It can be called an annulus. Some people will call it a donut. And I believe this textbook will call it a washer. So here, this is a slight modification of what we call the disk method. And this, because of this name that is often used, this will be called the washer method. Note that the disk method and the washer method are not different exactly. They are going to look very similar. The difference will be if your object is solid all the way through without any holes, you're going to use the disk method, where if there is some hole through the middle, whether it be a big one or a small one, we're going to end up using the washer method. Okay, so how do we do that? Well, notice that this is basically just the same method that we had before. You're going to find the solid disk and then add them all together. You say, yeah, but that's not a solid disk. Look, there's that hole missing in the middle. Yeah, but what's the shape of the hole? It's also a disk, but it's a smaller disk. Okay, so then find the smaller volume in the middle and then subtract them. This is called the washer method. The washer method says, okay, I'm going to go ahead and slice this up, and when I take a thin slice, it's going to give me a disk. Okay, so I know how to find the volume of a disk. It's going to be pi times the integral from a to b of f of x quantity squared dx. Oh yeah, but the problem is I don't have that hole in the middle. I'm missing that region. Okay, so what I need to do is I need to find the volume of the part that's missing. Okay, so that's going to be pi times, well, there's got to be a separate function, right? After all, this function f of x, that's the outer curve. That's the one that I use to find the big volume. I'm going to need a second curve on the inside that tells me where I'm going to find my smaller volume. It's going to be the edge that got cut out. Oh, so I'll call that g of x. And here, we're going to take the pi times the integral from a to b of g of x quantity squared dx. So I'm going to find one big volume, the volume of the whole thing, but then I'm going to find the volume of the part in the middle that's hollow. Basically, I'm going to find the volume of this cylinder. Oh, but then I'm going to find the volume of the small cylinder inside that's been cut out. Okay, so I found my two volumes. Okay, well, since I'm cutting it away, I'm subtracting it away. Let me subtract here. Note that because this is an integral from a to b with respect to x, and because this is an integral from a to b with respect to x, the linearity property of integrals allows me to do this. Here's pi. Let me factor that out. And now because I have an integral over the same bounds with respect to the same variable, I can go ahead and just subtract the two integrands. So we can write this as pi times the integral from a to b of f of x quantity squared dx f of x minus g of x quantity squared dx. We can merge it all together as one big integral. Note this one, unlike what we saw in the last section, these two must be in the correct order. Right? Having the absolute values here is not going to be sufficient to give you the correct result if you have those in the wrong order. So let's take a look at the example. I'm going to use the same one here, but now let me give it some values. Let me give it a function. Here's our outer curve, and that's given by y equals 4 minus 1/4 x squared, like that. And then I have an inner curve, and now it's going to be that flat line, and that's just going to be the line y equals to 2. And now I'm going to rotate all of that about the x-axis. So this line will revolve around, leaving us a hollow region inside of that space. And then this region will also revolve around, this curve will revolve around, leaving us the region inside of it. Something along those lines. All right. So now we want to find the volume of the solid. Remember, it is missing that hollow core. It looks something like this. I'm not about to go grab another piece of fruit, but what this reminds me of is anyone ever use an apple core? You take an apple and you take a small cylinder that's sharp along the edges and you push it through the apple and it pulls the core out. And you use that for making fruit salad and stuff like that. So that's what this is. This is an apple, and you push the core out of the middle. When I want to go find an apple, but I have apples. I just don't have a core. Oh, well. Gee, now I'm wondering if I can go get my drill. Okay, so we have these. So we can go ahead and orient them this way. Here, the volume is going to be given by pi. After all, it is still a revolution, so it's still there's still going to be disks. We still have a constant of pi. Integral from. Okay, so now what we want to know is where do these cross? Oh, well, that's simple enough. We just set them equal to each other. Whenever you don't know when two lines cross, you just set the two equations of the lines equal to each other. So let's see where that happens. Where do the lines cross? We're going to just set them equal to each other. So 2 equals 4 minus 1/4 x squared. I don't like fractions, so let me multiply everything times 4. That'll give me 8 is equal to 16 minus x squared. All right, that's gone now. Multiplied by 4. So now let me subtract 16 over to the other side, and that'll give me negative 8 is equal to, I can't read my own writing, that's an x, is equal to negative x squared, Or we can even say that's just x squared is equal to 8, which means that x is equal to either positive or negative the square root of 8. So that's what these numbers are. All right, that's going to be positive root 8 and negative root 8. Just like that. All right, so let me go ahead and do that over here. Let's not bunch all that together. So here volume is equal to pi times the integral from minus root 8 up to positive root 8 of, now we're going to take the outer function and we're going to square it. The outer function is just the one of the outer shell, the outer skin, all the way as far away from the axis as you can get. So here that's going to be given by this blue line, namely 4 minus 1/4 x squared. And that's being squared. Minus g, well, that's the inner curve, which in this case is just 2 squared dx. Okay. So now we can simplify and integrate. For most of these problems, the difficulty will be in setting this up. Once we write this equation out, everything else is usually just elementary algebra or some of our more basic integration techniques that we saw in Cal 1. It's making sure this is set up properly that is sometimes the difficulty. So this is pi times the integral from negative root 8 up to root 8. Let's see, we square this out. 4 minus 1/4 x squared times 4 minus 1/4 x squared. That'll be 16. 4 times 4 is 16, right? Minus 2x squared plus 1/16 x to the 4th power. Distribute that out, right? This times itself, and then we distribute. Minus, and then here I have a 2 squared, which is 4. So this is going to give us pi times the integral from minus root 8 up to root 8 of 16 minus 4. That's going to give us 12 minus 2x squared plus 1/16 x to the 4th power. All right, and here we go. We can now integrate that. That's going to be pi times, that's going to be 12x minus, that's going to be 2x to the 3rd divided by 3 plus, that one's going to be x to the 5th divided by 5, but then there's also a 16 down here. So 5 times 16 will give us 80. X to the 5th over 80. And that's going to be evaluated from minus root 8 up to root 8. Now, one thing you may remember from Cal 1, and that's whenever you are integrating with symmetric boundaries across an odd function. Here, if we're saying this is negative root 8 up to root 8, or negative 5 to 5, or negative 1 to 1, or really, as long as you have these symmetric around 0, one positive, one negative, if you're evaluating an odd function with these values here, that's just going to be double what you get if you evaluate it at the top one. All right? So here we can write this as 2 pi times 12x minus 2x to the 3rd over 3 plus x to the 5th over 80 evaluated at from 0 up to root 8. It has to do with the symmetry of that function. Basically, if you plug in 8 here, that's going to give you some result. If you plug in negative 8, it's going to give you the negative of that result. Oh, but you're going to take that result minus that result. So in other words, you're going to take this answer minus the negative of the answer. Oh, minus and minus makes that plus. So really, whatever this one was, you can just double it, and that'll get you both of them. All right? Now, that only works for an odd function, so be very mindful of that. If it's an even function, that doesn't work. Or if it's not even or odd, that doesn't work either. But here, that's an odd function, so things will work out nicely. Here, if you plug in 0, those are all zeros, so we don't care about that one. Just worry about root 8. So that's going to be 2 pi. Let's see, 12 times root 8. Now remember, root 8 is the same as saying 2 root 2. So that'll help us here in a moment simplify things out a bit. So that's 2 root 2 times 12. That's 24 root 2. Let's see, 2 root 2 to the third power. 2 to the third power is 8. Root 2 to the third power is 2 root 2. So it's going to be 16 root 2. So 16 root 2 times 2 is 32 root 2 over 3. Plus, and then if we substitute this in here, 2 root 2 to the fifth power. 2 to the fifth is 32. Root 2 to the fifth, that's 4 root 2. So multiply that together, that's going to give you 128 root 2 over 80, like that. And as intimidating as that might look, notice that all of these have a common factor of root 2, which we can just factor out now. So we can write this as 2 root 2 pi times, I factor out the root 2 here, so that's going to give me 24 minus 32 thirds plus, we can take 128 over 80. The top and bottom both divide by 16. So here, the root 2 has already been factored out, and that reduces to 8 over 5. And now we can put all that together. That's going to give us 2 root 2 pi times, let's see here. Common denominator of these two is 15. So then 15 times, okay, so give all these a common denominator of 15. So then we have 15 times 24 minus 32 times 5, 160, and then plus 24. And that'll give us 224 fifteenths. And finally, putting that all together, that'll give us, we just multiply those two. That's 448. That doesn't reduce, does it? 4, 5, 6, 7. No, it doesn't reduce. So that'll give us 448 root 2 times pi over 15, which may not be the nicest looking answer in the world, but it is our result. Note this is a volume. I probably should have mentioned that in the previous problem, right? Just like with area, we don't know the units, so we just generally say units squared. With volume, this should be inches cubed or feet cubed or miles cubed. But again, we don't know the units. So here we typically just say units cubed. And same thing with this one. We don't know the volume, so typically we just say units cubed. Just like that. All right. So let's go ahead and summarize the two methods that we've already seen. It's really just one method, but utilized at slightly different times. If ever you have an object where the solid region that you're revolving comes all the way down to the axis of rotation. You say, well, don't you mean the x-axis? Well, we're going to call it the axis of rotation because it won't always be the x-axis. So here, this is revolving around this. This is called the axis of rotation. And for now, we are looking at it being the x-axis, but it won't always be. So we just call it the axis of rotation. If you take this object and revolve it around, you'll notice that you have absolutely no holes anywhere in the middle. And so that's what's telling you to use the disk method. No holes or voids. No empty space, a void, an empty space. No holes or voids. That tells us that we're going to use the disk method. Each of these little slices is given by a disk. Hence the name, the disk method. And the disk method tells us that the volume is equal to pi times the integral from a to b of f of x quantity squared dx. On the other hand, if you have an object where there is a void, where there is some empty space in the middle, note that the empty space doesn't have to go all the way through. It can be somewhere in the middle. So for example, like this. Here, notice it does touch my axis of rotation, but there's some places where it touches and some places where it doesn't. So you don't have to have the entire empty space in the middle like we had in this problem where we had a whole core popped out. As long as there's any empty space in the middle, you're going to be using the other method, namely the washer method. So in this case, this cone in the middle would be empty space. You just stick your finger in there and there would be empty space in there, but this outer edge would be full. All right. So here this is the slice, and you'll notice that it's shaped like a little donut. Right? It's got a hole in the middle. The mathematical name for this, or a mathematical name for this, is a washer, whereas this is called a disc. And the washer method, you know that it's because there's a hole or a void. In this case, there's an empty gap in the middle there. That's telling us to use the washer method. And here, that's going to be V is equal to pi integral from A to B of f of x quantity squared minus g of x quantity squared dx, where f of x is this outermost curve, g of x is the innermost curve, the one that is giving you the region that is empty, the void in the middle, the empty gap in the middle. All right. So now let's take a look at an example where the axis of rotation is not the x-axis. Does that mean it has to be the y-axis? Well, no, actually it doesn't. It can be the x-axis, it can be the y-axis, but it can also be something else. So here we're going to look at two examples, one where it's the y-axis and one where it's something else. So let's go ahead and consider this object here. This is the curve y equals 2x squared. And in fact, let's go ahead and draw that out. Y equals 2x squared. And then this is the line x equals to 2. Okay. But now, instead of revolving this way, we're going to revolve this way. We're going to revolve around the y-axis. So find the volume of the solid made by revolving, oops, I don't know how to spell, by revolving, there we go, by revolving the region, and here it's that region there, about the y-axis. So these problems in your homework, in your assignment, you're going to see they're going to give you a region. Some of the times they'll actually graph it for you. Other times they'll just tell you the equations and you graph it yourself. And then they're going to tell you where to rotate around. So in this case, you rotate around the y-axis, same thing, the x-axis, same thing here. However, there are going to be some times where you're going to rotate around something else. So here you're rotating about the y-axis. All right, so here, when you rotate, you're not going to get an object that's above the x-axis and below the x-axis. Rather, you're going to get an object that's to the left and to the right of the y-axis. So here, your object's going to look not this way, but it's going to look like it's rotating this way. What that means is you're going to have these discs stacked not left to right. Here, they're going from left to right. Here, we're going to have these stacked top to bottom. Just like that. Okay, so now what's the difference going to be here? Well, one major difference is, remember that over here, this dx came from the variable that told us the thickness of our disks. This dx came from this delta x. But the reason we had delta x in the first place was because that told us the thickness of each of these little disks. Well, notice now that the disks aren't being measured left and right. The thickness of each one of these little disks is up and down. So here, instead of having integrals with respect to x, you're going to notice this is going to be an integral with respect to y. So that is one major difference between the change in the axis of rotations. Here, I'm going to go ahead and state it here. If, now this is for the disk or the shell method, shell. I'm getting ahead of myself. That's for the next section. The disk or washer method. This will be different for the shell method, which will come in the next section. But for the disk or washer method, if the axis of rotation is horizontal, which means it could be the x-axis or it could be some other line, as long as it's horizontal. It can be the x-axis or anything parallel to the x-axis. If the axis of rotation is horizontal, it's the x-axis or it's parallel to the x-axis, then you're going to end up integrating with respect to x. On the other hand, if the axis of rotation is vertical, which is either the y-axis or parallel to the y-axis, then you integrate with respect to y. With respect to y. Pay very careful attention to this. By the end of this section and the next section, we're going to have three different methods. All three of them are going to look very, very similar. And sometimes the only difference is going to come down to what variable of integration do I need or which variable of integration do I have. This is the single biggest mistake people make when looking for volumes of solids, and that they will get their variable of integration wrong. And if you have the wrong variable of integration, you'll have the wrong method, which means you'll have the wrong answer. So be very mindful of this. Make sure that these are things that you don't forget. These are central to setting these up correctly. If you remember this, everything else is just, oh, I just compute an antiderivative and plug in some numbers. If you don't remember this, nothing else is really going to happen. All right. So in this case, we have an axis of rotation that's vertical. In this case, it's the y-axis, but even if it was parallel to the y-axis, it will still be the same thing. We're going to integrate with respect to y. Okay, so that's going to be an integral from a to b of f of y dy. Okay, yeah, just dy, but f of y, what is that thing? Oh, and don't forget your pi, right? Pi times an integral. F of y, what is an f of y? Well, it's a function of y. How do you do that? We've never had functions of y. We've only ever had functions of x. Well, yeah, so invert it. Here, the reason this is a function of x is because y is given by some expression that involves x. If we want a function of y, we invert this. Divide both sides by 2. That's going to give us y over 2 equals x squared. And then take the square root of both sides, which gives us x is equal to square root of y over 2. It should be plus or minus, but notice this region is entirely positive. We only care about the positive values here, to the right and above the origin. So this really should be plus or minus, but we're only going to care about the positive part. So here, that's the function of y. That's why it's important to have the variable of integration correct. It's not just, oh, let me replace x's with y's or y's with x's. That would be trivial. The important part is that we have the function set up correctly. If you use this, Even if you replace that with a y, it's going to be wrong. We need this form. So once we have that squared away, the rest of this is easy, relatively speaking anyway. This is pi integrated from a to b. Now remember, it's no longer describing the x values. Up here, a and b, we're going from left to right. A and b here are going top to bottom. So that's going to be from a up to b, not left to right along the x-axis, but bottom to top along the y-axis. So here that's 0 up to 2, right? X equals 0, x equals 2. No, that's not right. Sorry, I labeled that incorrectly. That should be, that's a horizontal line, so it should be y equals 2. My apologies. It's not going to change anything we've done, but that really should be y equals 2 since it's horizontal. So that's going to be a is 0 up to a is 2. Oh, sorry, up to b is 2. 0 to 2. F of y is going to be this function here. So that's going to be the square root of y over 2 dy. And that'll give us the volume. All right, so let's go and compute that thing. That'll be pi integral from 0 to 2. Let's go ahead and rewrite this a little bit. We're going to write this as square root of y over square root of 2 dy. That's a constant. Let me just pull that out. So it's going to be pi over root 2 integral from 0 to 2 of the square root of y dy. Like that. You can think of y as being to the 1/2 power. That's the same thing as saying square root. So here we can write this as, and while we're at it, let's rationalize that denominator. Well, I'll rationalize at the end because I may still have some other stuff to do. So here I'm going to take this square root of y, and I'm going to write it as y to the 1/2 power. Not that we have to, but it's generally simpler to remember how to integrate if this is written as a exponent. And now I can add 1 to that power and divide by the new power. So this will be pi over root 2, y to the 3/2 divided by 3/2, which is the same as times 2/3. And that's going to be evaluated from 0 up to 2. Okay. Obviously, if you just plug in 0, that's 0, so we don't worry about that one. So the only thing we worry about is the number 2. So that's going to be pi over root 2 times 2/3 times 2 to the 3/2, which is 2 root 2. All right? 2 to the 2/2 plus, 2 to the 2/2 times 2 to the 1/2. Well, 2 to the 2/2 is just 2. 2 to the 1/2 is the square root of 2. And those nicely cancel out. I wasn't sure that was going to happen, but oftentimes when you have radicals, things tend to simplify out in a lot of these problems. And so here we have 4 pi over 3. And that's our result. Keep in mind these are units cubed, cubic units, because it's a volume. Notice, setting these up is the complicated part. Once it's set up, we haven't seen any integrals that were anything more than 1 or 2 lines. Quick, simple integration. Okay, let's take a look at one more example. This time, we've seen 2 examples where we rotate around the x-axis. One's where it was a disk method, the other was a washer method. Now we've seen rotation around the y-axis. Let's see what happens when we rotate around something that's neither of those axes. So for our next example, let's find the volume. Find the volume of the solid generated by revolving the region that is bound by the equations y equals x squared and y equals 4x minus x squared about the line y equals 5. All right, so here they don't give us any illustrations at all, but if we need to, we can draw our own. That's okay. All right, here, let's actually go ahead and draw it. It does tend to make things a little easier to talk about if we are looking at the same thing. Y equals x squared. Well, that's just a parabola. Looks like that. Okay. All right, that's also a parabola. Notice that it's facing down because you got negative x squared. The zeros of this function are 0 and 4. All right, you could always factor that out as being x times 4 minus x. And the zeros are going to be 0 and 4. So that's going to be a parabola facing down. Here's 0 and here's 4. And my parabola goes up and comes back down over here. Okay. So now we want to find the volume of the solid generated by revolving the region bound by those two graphs. Well, here's the region bound by those two graphs. So that's what I'm about to start revolving. Okay, what am I revolving that around? The x-axis or the y-axis? Well, neither. We're revolving that around the line y equals to 5. Okay. What are these points? So let's find out what those points are. Where these two cross, let's see. Let's take x squared and set it equal to 4x minus x squared. We can go ahead and add the x squared over here to give us 2x squared. And then we'll subtract the 4x over this way. 4x is equal to 0. And then we can factor out a 2x from both of those, giving us 2x times x minus 2 equals to 0. And that gives us x equals to 0, which we already knew. Those crossed at 0. And we get x equals to 2. Okay, so that's going to be 2 right there. And what's the y value? Well, let's just plug in the number 2. 2 squared is 4. Okay, so that's going to be 4. And you say, well, why did you choose that one? Well, it works either way. Remember, that point is on both curves. If you plug it in right here, 4 times 2 is 8. 2 squared is 4. 8 minus 4 is 4. Or plugging it in right here, 2 squared is 4. Either way, it's on both. Okay, so if that's 4, we're revolving around the line y equals to 5. Okay, so 5 will be slightly higher. So that is the line we're revolving around. Okay, notice that we have a big gap between our region and our axis. Because there's a big gap, a void, a space, whatever you want to call it, that means we're going to use the washer method. If there's any space between your region and your axis of rotation, you have to use the washer method. So because we will have a void, a space, a gap, an empty region of space, whatever you want to call it, we use the washer method. And because the axis of rotation is horizontal, it's not the x-axis, but it is parallel to the x-axis. Notice it's not the x-axis, but it is parallel to the x-axis. Because it's a horizontal axis of rotation, for the either disk or washer method will integrate with respect to x. Because axis of rotation is horizontal, we integrate with respect to x. Okay? So that's going to be our setup. We're going to use that method using that variable. All right, so now we just start plugging things in and get our result. We're going to take pi times the integral from a to b. Okay, well, since we're doing everything with respect to x, that means a and b are going left and right. Oh, well, we already found those. From left to right, this goes from 0 up to 2. Yeah, I know this curve goes out to 4. But we don't care. We don't care about this part right here, the region that we're revolving. So from 0 to 2. You say, well, yeah, but it goes up to 4. But again, we only care about the x variable. So from 0 to 2. So that's pi times the integral from 0 to 2 of the outer function minus the inner function. Now here is another point of contention, a point of confusion. Some people will want to put this curve right here as the first function and this curve down here as the second function. That's not true, because remember, the first function you're going to put is the one that serves as the outer edge of your region. In our previous example, over here, sure, this, maybe let me use the one that has the void in it, the gap in there. Sure, this one on top goes first, and this one on the bottom goes second. But that's because that's the one furthest away from the axis. So that's the one on the outside of my solid. But over here, since I'm not rotating around the x-axis, since I'm rotating up here, look what your object looks like. If you rotate it, it looks something like this. That's what that object looks like. You might say, what is that object? It's the shape of my favorite teacup. I'm going to give you guys a tour of my house, one object at a time, I think. That's exactly what that shape is. Notice the outer edge flares out. It's flat on the bottom, right here. It's flat and wider on the top. And if you look inside, it's hollow. Right? The only difference between this object and this object is that my object has a bottom, whereas this one, I should cut out the bottom of this, and then I'd have exactly that object. But this is my favorite teacup. I'm not cutting it out. So, close enough. All right. So here, what are we going to do? We're going to take the distance from the axis of rotation to the outer edge. And notice it's not this one. For this object, this one, even though it's above this one, it's the inner edge. This edge right here represents the inside of my teacup. Yeah? This one represents the outer edge. Okay, so be very mindful of that. It's not always the top one goes first. It's whichever's furthest from the axis goes first. Okay, so you're going to have your f squared minus your g squared. So let's start with that one. What is f? Well, again, f is the distance from the axis of rotation to out here. Notice that you're not starting at 0 anymore. You're starting at 5. So what you want is the distance from this horizontal line down to this curve. Okay, so you want the distance starting from 5 down to this curve. So you're going to take 5 minus the curve. Let's see, which curve was that? That was x squared. Your axis of rotation minus the curve gives you the distance between the two of them. And then don't forget that's being squared. Minus, and then we're going to do the same thing for the inner curve. This distance from the axis to this inner curve, well, again, that's going to be 5 minus that curve. The distance between 5 and the curve is 5 minus the curve. So 5 minus 4x minus x squared. And the whole thing is squared. So now let's simplify that out and we'll get our answer. So this will be pi, integral from 0 to 2. We can square this out, and that'll give us 25 minus 5x squared minus another 5x squared is minus 10x squared. Plus, let's see, negative x squared times another negative x squared is positive x to the 4th. Minus, here we can square this part out. Let me distribute my negative first to keep that from getting a little, keeping that from getting a little confusing. Let's distribute the negative first. That way I have fewer things to worry about. Minus x, minus 4x. Double negative makes that a plus x squared. And now that thing's being squared. And that is going to give us, let's see, pi integral from 0 to 2 of, and here I'm just rewriting that part, 25 minus 10x squared plus x to the 4th minus this times itself. Oh, let's see, that's going to give us 25 minus 40x squared. Oh no, that should just be 40x plus 26x squared minus 8x to the third plus x to the fourth. And if you're wondering how I did that so quickly in my head, I didn't. I have a piece of paper on the side of my desk that I do my calculations on. I figure you guys didn't want to see me multiply this times itself, you know. Okay, 5 times 5, 5 times minus 4x, 5 times x squared. I don't think you'll want to see me do the multiplication here. So that's the result of multiplying. And now here you notice that a few things subtract away. 25 minus 25, that's gone. X to the fourth minus x to the fourth, that's gone. These don't go away, but they do combine since they are like terms. So you can write this as pi, integral from 0 to 2 of, let's see. Let me write these in order. So minus a minus 40x, that's just 40x. Now let me put the quadratics. That's going to be negative 10x squared minus 26x squared is minus 36x squared. Minus a minus makes that a plus 8x to the third. And after a bit of setup, which as I mentioned that sometimes is the hardest part, this is nice and simple relative to everything else we see. So this is pi. Integrating 40x with respect to x will give us 20x squared. Integrating negative 36x squared will give us negative 12x to the third. And integrating 8x to the third will give us 2x to the fourth, and that's all evaluated from 0 up to 2. Obviously, plugging in 0 into all of these makes them 0. All right, 0 times 0 times 0. Okay, whatever. So we'll just worry about the 2 now. So that's going to be pi times, let's see, 2 squared is 4 times 20 is 80 minus 2 to the third is 8. 8 times 12 is 96. And then 2 to the fourth times another 2, let's see, that's 32. Oop, like that. Let's see, that's what? 112 minus 96. That'll give us 16. And so that gives us our volume. Keep in mind that since that is a volume, our units are cubed, so this is units cubed. All right. Note, whether or not it has a void tells us to use either the disk or the washer method. And the direction of the axis of rotation tells us which variable of integration we're going to use, x or y. The distance from the axis to the outer edge goes first, then squared, minus the distance to the inner edge goes next, then squared. Do some expanding, and then we integrate. Once we integrate, we end up with our volume in units cubed. And that's it. That's it for the section. In the next section, we're going to be looking at a different method for finding volume. Again, it's not a different thing that we're finding. It's a different way of organizing it. And the reason we want a different method is because once we have the, here we can consider this one method, the washer disk method. They're essentially the same. Once we have the washer disk method and the shell method that we'll see in the next section, one of those techniques will always be nice and simple compared to the other one. Right? Sometimes they'll both be at least a little bit messy, but you'll always have one that's noticeably simpler than the other. In a few cases, there's going to be one which is so much harder than the other that it's practically impossible. Not that it's actually impossible, just practically so. It's too difficult to pull off in any reasonable amount of time with or without a calculator. So we'll have another method to simplify, to give ourselves some options and to simplify the computations, and in some cases just to make the computations possible. They won't be possible one way, but it'll be okay the other way. So that is it for this section. If anybody has any questions, comments, or problems, please make a note of those and let me know during our next office hours or during our next meeting. And I hope everyone has a nice day.